Hi, I'm Ohad. I'm from Tel Aviv University, and I'm advised by Jonathan Barat. I'll be presenting the retrieval pre-trained transformer, worked by me and my advisor. I'm very excited to show it and share it with all of you guys. So I think since ChatGPT came out, the workflow of many of us changed dramatically, but these models still have many weaknesses. I'll try and argue that retrieval gives us pretty good solutions to many of these weaknesses. So for example, while LLMs can answer correctly many questions, the answer to many questions change, making their knowledge stable. LLMs tend to be more accurate when recalling widely known information, but performance drops off significantly when dealing with obscure facts. And as of recently, they are able to handle long sequences, but it's often very expensive and slow. So retrieval solves these problems. In contrast with regular LMs that are able to use a large corpus only during training, retrieval augmented language models can access external data also during test time. So retrieval is awesome and enables language models to use up-to-date information. It solves the long tail problem, since searching the web yields highly specific information. And it makes long context tractable by focusing only on the relevant context per query. So let's example two representatives to retrieval augmented language modeling. A prominent line of work can be represented by retro from Borgard et al., which incorporates retrieval results in the intermediate layers of the LMs. But one downside is that the retriever itself is frozen. Conversely, another noteworthy work is Trime by Zong et al. Trime does train the retriever and language model jointly, but it has two key limitations. One, it relies on shallow probability interpolation to integrate retrieval results. And two, it uses lexical supervision to train the retriever. Our proposed method addresses these limitations. Like retro, we perform retrieval at intermediate layers, allowing for deep integration of retrieval results. And like Trime, we train the retriever and language model jointly, where our retriever is trained with semantic supervision, as we will soon see. Our retrieval pre-trained transformer, or RPT, is an autoregressive decoder-only language model that can self-retrieve its own past representations. RPT is comprised of three parts. The lower decoder, it's a standard autoregressive transformer. The retriever component retrieves past representations, and the upper decoder that deeply integrates these retrieved representations in the upper layers. This allows us to train our retriever and language model jointly. We evaluate our architecture on language modeling domains requiring long-range understanding, such as books, Python code, and mathematical papers. Let's dive into the details. So we take a long sequence and divide it into chunks, C1, C2, and so on. We also divide it into segments. In the figure here, we have a green, a yellow, and a blue segment, each containing 3 chunks. Within each segment, we independently apply causal tension in the standard fashion inside the lower decoder. Here, the blue segment cannot see the yellow and green segments. But while blue can't see them via causal attention, it will be able to see them via retrieval and chunked causal attention. We term these retrievable chunks, i.e. prior chunks that the language model cannot see with standard attention. So the retrievable chunks of the blue chunk are all 6 green and yellow chunks. Let's see how retrieval is performed. After applying the lower decoder, we pass these representations over to the retriever. The retriever pulls and projects these representations into query and key chunk representations. And we perform a dot product between the corresponding key and query and key representations. And we call this dot product the query-based score. During inference, for every query chunk, we retrieve the top k retrievable chunks as neighbors and pass these representations to the chunk cross attention layers in the upper decoder. But top k is non-differentiable, so we have an implicit stop grad operation. So how do we train the retriever? We ask the question, given a text chunk and its continuation, what text chunks would be good neighbors? Our answer is check text chunks that increase the probability of the continuation. We use some reference language model for calculating the probability. Here, C201 is our query chunk, and C202 is its continuation or target chunk. We pass the reference language model a query chunk and a candidate retrievable chunk, and calculate the probability of the target chunk. So simple probability isn't good enough because we might include chunks that aren't very good supervision. So to improve the quality of the supervision, we only use candidate chunks if they are better than some baseline chunk. And a natural choice here is the most recent chunk, C200. We call this log ratio the target base score. And for every chunk, we compute it for the top 20 BM25 results. And say it's a positive chunk if the target base score is greater than 0. Very, very simple. So we train with the standard language modeling objective and add an auxiliary objective for training the retriever. For a given query Q, we have the query base score as our prediction from the retriever, and the target base score as our supervision. We employ a margin-based pairwise ranking loss from the retriever literature, like very, very standard. And for a pair of chunks, our loss is non-zero if the target score disagrees with a margin of 1 with the ranking of the query-based score. Let's see some empirical evaluation. So we carried out an evaluation of RPT on 4 datasets. First is books free. It's part of the pile, and it contains literary and non-fiction works from various domains. Next is PG19, introduced by Ray et al. It consists of books from Project Gutenberg. It's widely used for benchmarking long-range reasoning. And then we have CodeParrot, which is a corpus of clean deduplicated Python code. Finally, we have a corpus of mathematical preprint papers from arXiv. Okay, so let's go over our results. Our first baseline is Transformer Excel, which is a widely used long-range baseline. In this figure, we have a relative percent improvement in perplexity against the Transformer Excel results. Our first retrieval baseline is our re-implementation of retro with an unsupervised BIM25 retriever. Our second retrieval baseline is RPT-Lex, which is an RPT model that uses lexical supervision. This is our TRIME analog. Compared with both of these baselines, we see noticeable gains on arXiv, books free, and PG19. Compared with RPT-Lex, our results show the importance of our semantic supervision, especially on books free and the arXiv. On code, retro plus BM25 has parity with RPT. And later we'll see an analysis of that explains why this occurs. So our next 2 baselines are memorizing transformers and block recurrent transformer, 2 strong long-range LMs from Google Research. Performance is again either comparable or better. Another thing is now as test time compute methods are getting increasingly popular, RPT can also increase its test time compute by increasing the number of neighbors. Indeed, we see that more test time compute leads to better performance as we increase the number of neighbors from 2 to 4. Finally, we have our oracle. Here we see that with a better retriever, there is a lot of headroom for improvement. Let's see a bit of analysis. We computed our supervision on the top k chunks with k equals 20. So, and we only use the supervision if this log ratio up here was positive, or as a function of k, if age of 20 was positive. A natural question to ask is what happens as we increase k from 1 to 20? So we consider more candidates. So this function increases monotonically. This allows us to compare how fast h of k increases per dataset. As we see in green, h of 2 for code parrots is already quite high, corresponding to around 10% of relative improvement in the target probability. Compare that with PG19 and Books 3, where it is closer to 0. This suggests that for code, lexical retrieval alone is quite effective, which explains why retro has similar performance with RPT on code. In conclusion, RPT is trained jointly to retrieve its own representations with a semantic objective. Thank you.